What if everything you think you know about the beginning of the universe is wrong? What if the most celebrated, most tested, most trusted theory in all of modern science has a crack running through its very foundation, and almost nobody is talking about it? What if I told you that right now, at this very moment, ancient light that has been traveling across the cosmos for 13.8 billion years, is passing through your body, through the walls of your room, through the screen you are watching this on, and that this light carries a message from the very birth of the universe itself. And that message says, something is broken, something does not add up. Something in the story of how our universe began is either missing or fundamentally wrong. Let me ask you a question. If you could travel back in time, all the way back, not 1,000 years, not 1,000,000 years, not even 1,000,000,000 years, but 13.8 billion years, all the way back to the moment the universe was born, what would you find there? Would you find an explosion, a flash of blinding light, an infinite darkness? Or would you find something so bizarre, so alien, so completely beyond human comprehension that no language on earth has the words to describe it? And what if I told you that you do not need a time machine to see it? Because a snapshot of that moment, a photograph of the infant universe, is literally surrounding you from every direction right now, frozen in the faint glow of microwave radiation that fills every cubic centimeter of space in the observable cosmos. This is the cosmic microwave background, the oldest light in the universe, the afterglow of creation itself. And for decades, it has been the crown jewel of modern cosmology, the single most powerful piece of evidence that the Big Bang actually happened. Scientists have studied it, mapped it, measured it with breathtaking precision, and every time they looked at it, it confirmed what the Big Bang theory predicted. The universe began in an unimaginably hot, dense state. It expanded, it cooled, and eventually, about 380,000 years after the beginning, it became transparent enough for light to travel freely. That light has been traveling ever since, stretched by the expansion of space itself into microwave wavelengths, and it bathes the entire observable universe in a faint, nearly uniform glow, at a temperature of just 2.725 degrees above absolute zero. It is beautiful. It is elegant. It is the most perfect black-body spectrum ever measured in nature. And it should be the end of the story. Case closed. The Big Bang happened. The evidence is overwhelming. But it is not the end of the story. Because when scientists looked more closely, when they built better instruments, launched more sensitive satellites, and created more detailed maps of this ancient light, they found something they were not expecting. They found anomalies. Not just one anomaly, but several. Patterns that should not be there. Alignments that violate the fundamental assumptions of the Big Bang theory. A mysterious cold spot so vast and so inexplicable that some physicists believe it could be the scar left by a collision with another universe. An eerie alignment of the largest patterns in the cosmic microwave background that scientists have given a chilling name, the axis of evil. A lopsidedness to the universe that suggests one half of the sky is fundamentally different from the other. A disagreement between what the ancient light says and what the distribution of matter in the universe actually shows. And most recently, a brand new discovery, a subtle rotation in the polarization of this ancient light that breaks one of the most sacred symmetries in all of physics. Each of these anomalies, taken individually, could perhaps be dismissed as a statistical fluke, a coincidence, an artifact of imperfect data. But taken together, they form a pattern that whispers something deeply unsettling to anyone who cares to listen. The Big Bang theory, the most successful cosmological model ever devised, may be incomplete. It may be an approximation of a deeper truth that we have not yet discovered. And the cosmic microwave background, The very evidence that was supposed to confirm the Big Bang beyond all doubt may be the thing that ultimately forces us to move beyond it. In this video, we are going to take the deepest, most thorough dive into this mystery that you have ever seen. We are going to start from the very beginning. We are going to understand what the cosmic microwave background actually is, how it was discovered in one of the most remarkable accidents in the history of science, what the Big Bang theory predicts about it, and then, piece by piece, anomaly by anomaly, we are going to explore everything that does not fit. We are going to look at the cold spot, the axis of evil, the hemispherical asymmetry, the cosmic dipole anomaly, and the brand new phenomenon of cosmic birefringence. We are going to examine the latest research from 2025 and 2026, including a groundbreaking study from Oxford University that suggests the universe may be fundamentally lopsided, a radical proposal from Chinese and German researchers that part of the cosmic microwave background may not even come from the Big Bang at all, and startling new evidence that the polarization of the oldest light in the universe has been rotated in a way that violates parity symmetry and points toward completely new physics. By the end of this journey, you will understand why some of the world's most brilliant physicists believe we may be standing on the edge of a scientific revolution, a revolution as profound as the one that took us from Newton to Einstein, from classical physics to quantum mechanics. The next decade could change everything we think we know about the universe. And it all starts with a faint hum of microwave radiation that has been whispering to us for 13.8 billion years. So, if you are ready, let us begin. But first, let me welcome you. If you are new to this channel, my name is your guide through the deepest mysteries of the cosmos. This is a place where we do not just scratch the surface. We go deep. We explore the universe with the rigor of a scientist and the wonder of someone seeing the night sky for the very first time. We take complex, cutting-edge physics, and we make it accessible, understandable, and absolutely fascinating. Because I believe that the universe belongs to everyone, not just to people with PhDs. If you love science, if you love having your mind blown, if you love understanding how reality actually works, then you are in exactly the right place. And I have one small request before we dive in. If you enjoy this kind of content, if you value deep, thorough explorations of the biggest questions in science, please take 1 second right now and hit that subscribe button. Tap the bell icon so you never miss a video. It sounds like a small thing, but it makes an enormous difference for this channel. It helps us reach more curious minds, create more content like this, and build a community of people who genuinely care about understanding the universe we live in. Also, I want to hear from you. Drop a comment right now and tell me where you are watching from. What country, what city, what time is it where you are right now? I'm always amazed by how our community spans the entire globe. Every time I read the comments, I see people from Pakistan, India, the United Kingdom, the United States, Saudi Arabia, Germany, Australia, Canada, Bangladesh, and dozens of other countries. It reminds me that curiosity is universal. It does not care about borders or languages or time zones. So, tell me where you are, and let us see how far our community reaches today. One more thing. I know this is going to be a long video, a very long video, but I promise you, every single minute is going to be worth your time. This is not filler. This is not fluff. Every sentence in this video has been researched, every concept has been verified, and every twist in this story is going to make you see the universe differently. So grab a cup of tea or coffee, get comfortable, maybe put on some headphones, and let us take this journey together. Now, let us start at the very beginning, and I mean the very beginning. Let us understand what the cosmic microwave background actually is, because if you do not understand this, nothing else in this video will make sense. And trust me, once you truly grasp what the CMB is, you will never look at the sky the same way again. To understand the cosmic microwave background, we first need to understand something about light itself. When most people think of light, they think of the visible light that our eyes can see, the rainbow of colors from red to violet that illuminates our world. But visible light is just a tiny sliver of a much larger phenomenon called the electromagnetic spectrum. Electromagnetic radiation comes in a vast range of wavelengths and frequencies, and the part we can see with our eyes represents only a minuscule fraction of it. On one end of the spectrum, you have radio waves, with wavelengths that can be meters or even kilometers long. Then, as the wavelengths get shorter and the frequencies get higher, you move through microwaves, then infrared radiation, then visible light, then ultraviolet, then X-rays, and finally, at the extreme high-energy end, gamma rays, with wavelengths smaller than an atomic nucleus. All of these are forms of the same fundamental thing: electromagnetic radiation. They are all waves of oscillating electric and magnetic fields traveling through space at the speed of light. The only difference between a radio wave and a gamma ray is the wavelength and frequency. And this is crucial to understand, because the cosmic microwave background is electromagnetic radiation in the microwave part of the spectrum, with wavelengths of about 1 to 2 millimeters, corresponding to a frequency of about 160 gigahertz. It is invisible to our eyes, but it is absolutely real, and it is everywhere. Now, why is the cosmic microwave background in the microwave range specifically? Why not visible light, or radio waves, or X-rays? The answer to this question takes us back to the very beginning of the universe, and it involves one of the most important concepts in all of cosmology, the expansion of space and the resulting phenomenon known as cosmological redshift. When the universe was very young, it was unimaginably hot. In the first fraction of a second after the Big Bang, temperatures were in the trillions of degrees. As the universe expanded and cooled, the temperature gradually dropped. By the time the universe was about 380,000 years old, it had cooled to about 3,000 degrees Kelvin, which is roughly the temperature of the surface of a cool red star. At this temperature, the universe was glowing with visible light and infrared radiation. If you could have been there to see it, the entire sky would have been a brilliant, uniform orange-red glow in every direction, with no darkness anywhere. It would have been like being inside a furnace that extended to infinity. But here is the key. Since that moment, 380,000 years after the Big Bang, the universe has been expanding. And as the universe expands, the wavelengths of light traveling through it get stretched. This is cosmological redshift. Light that was emitted as visible, orange-red light 13.8 billion years ago, has had its wavelength stretched by a factor of about 1,089 as the universe has expanded over billions of years. That stretching has shifted the light from the visible range all the way into the microwave range. The temperature of this radiation has correspondingly dropped from about 3,000 Kelvin to just 2.725 Kelvin, which is 2.725 degrees above absolute zero, the coldest possible temperature. So the cosmic microwave background is literally the cooled-down, redshifted remnant of the first light that was ever able to travel freely through the universe. It is the oldest light we can possibly observe. Nothing in the universe is older, at least nothing that we can detect with telescopes that observe electromagnetic radiation. And it is not just coming from one direction. It is coming from every direction in the sky, uniformly, because the entire universe was glowing at that time, in every direction, everywhere. But now we need to understand something even more fundamental. Why was the universe opaque before 380,000 years? And why did it suddenly become transparent? What happened at that moment that released this light and allowed it to travel freely for the next 13.8 billion years? The answer lies in the physics of what happens when the universe cools below a certain critical temperature. In the very early universe, the temperatures were so extreme that matter could not exist in the form we know it today. Atoms could not form because the environment was too energetic. Any time an electron tried to bind to an atomic nucleus, a proton or a heavier nucleus, a high-energy photon would immediately come along and knock the electron free again. This meant that the universe was filled with a hot, dense plasma, a soup of free electrons, protons, helium nuclei, and photons, all interacting with each other furiously. The photons were constantly scattering off the free electrons, bouncing around in random directions, unable to travel in a straight line for any significant distance. The universe was opaque, like a thick fog, because light could not travel through it. But as the universe expanded and cooled, there came a moment when the temperature dropped to about 3,000 Kelvin, the threshold at which electrons could finally stick to atomic nuclei without being knocked free by photons. This moment is called recombination, although it is a somewhat misleading name because the electrons and nuclei were combining for the first time, not recombining. When this happened, the free electrons that had been scattering the photons suddenly disappeared, absorbed into neutral atoms. The fog cleared. The universe became transparent, and all those photons that had been trapped bouncing around in the plasma were suddenly free. They streamed out in every direction, carrying with them a snapshot of the universe at that exact moment, like a flashbulb going off at a cosmic scale. This event, the moment when the universe became transparent and the cosmic microwave background was released, is called the surface of last scattering. It is called this because it represents the last time those photons interacted significantly with matter. After that moment, they just traveled for 13.8 billion years across the expanding universe, carrying information about the conditions at the time they were released. Think of it like this. Imagine you are standing in an incredibly dense fog. You cannot see more than a few centimeters in any direction because the light keeps scattering off the fog particles. But then, suddenly, the fog lifts all at once, everywhere, simultaneously. In that instant, you can see, and the light from the last surface of the fog, the last boundary where the fog existed, reaches your eyes and shows you what that boundary looked like. That is what the cosmic microwave background is. It is the light from the surface of the last scattering, the boundary between the opaque early universe and the transparent universe that followed. It is the baby photograph of the cosmos, taken when the universe was just 380,000 years old, and it has been traveling toward us ever since. Now, I want you to appreciate just how extraordinary this is. Every time you see a map of the cosmic microwave background, those beautiful, colorful, oval-shaped images that show tiny splotches of slightly warmer and slightly cooler regions, you are looking at the oldest thing that human beings can ever observe with light. You are looking at the universe as it was 13.8 billion years ago. Not galaxies, not stars, not planets, because none of those things existed yet. You are looking at the primordial plasma itself, the raw material from which everything in the universe would eventually be built. It is humbling. It is awe-inspiring. And it is real. It is not a simulation, not an artist's impression, not a theoretical prediction. It is actual data, actual light, that has been traveling across the cosmos for longer than the Earth, the Sun, the Milky Way, or anything else you have ever known has existed. And here's another fact that I want you to sit with for a moment. The cosmic microwave background is not just historical. It is present. It is here, right now, all around you. About 1% of the static you used to see on an old analog television, that random snow of white and gray dots, was caused by the cosmic microwave background. You were literally watching the afterglow of the Big Bang on your TV screen without knowing it. Every cubic centimeter of space in the observable universe contains approximately 411 photons from the cosmic microwave background. That means, right now, as you are watching this, hundreds of these ancient photons are passing through your body every second. They are the most abundant photons in the universe, outnumbering all the photons produced by all the stars in all the galaxies that have ever existed. When you look up at the night sky and see the light of distant stars and galaxies, you are seeing a tiny fraction of the total photons in the universe. The vast, overwhelming majority of photons are from the CMB, invisible to your eyes but filling all of space with their ancient whisper. Let us talk about the temperature of the CMB in more detail, because this is one of the most remarkable aspects of the whole story. The cosmic microwave background has a temperature of 2.725 Kelvin, which means it is just 2.725 degrees above absolute zero, the lowest temperature theoretically possible. This temperature is incredibly uniform across the entire sky. No matter which direction you point a sensitive microwave detector, you measure essentially the same temperature. The uniformity is staggering. The temperature varies by only about 1 part in 100,000 from one direction to another. That means if you could turn the CMB temperature into a dollar bill, the variations would be less than 1/1000th of a penny. It is the most uniform thing we have ever measured in nature. But this uniformity itself is remarkable because it tells us something profound about the early universe. For the temperature to be the same in every direction to such extraordinary precision, the entire observable universe must have been in thermal equilibrium at the time the CMB was released. Everything was at the same temperature everywhere, in every direction. This seems natural at first, but when you think about it more carefully, it raises a deep and disturbing question, a question we will come back to later when we discuss inflation theory. Now, within this extraordinary uniformity, there are those tiny variations, fluctuations of about 200 microkelvin, or about 1 part in 100,000. These are called the CMB anisotropies, and they are the most important features in the entire cosmic microwave background. Because those tiny temperature variations correspond to tiny density variations in the primordial plasma. Regions that were slightly denser and slightly hotter appear as slightly warmer spots in the CMB, and regions that were slightly less dense and slightly cooler appear as slightly cooler spots. And those tiny density variations are the seeds of everything. Every galaxy, every star, every planet, every person who has ever existed owes their existence to those minuscule fluctuations in the primordial plasma 13.8 billion years ago. The slightly denser regions had slightly stronger gravitational pull, which attracted more matter over time, which made them even denser, which attracted even more matter, in a cascading process that, over billions of years, built up the galaxies, galaxy clusters, superclusters, and the vast cosmic web that defines the large-scale structure of the universe today. Without those fluctuations, the universe would be perfectly smooth and featureless. No clumping, no structure, no galaxies, no stars, no planets, no life. Just a perfectly uniform, slowly cooling gas expanding into eternity. The fact that the universe is not perfectly smooth, that it has this tiny amount of lumpiness, is the reason we exist. And the astonishing thing is that these fluctuations appear to have originated from quantum mechanics. In the very early universe, during the epoch of inflation, which we will discuss in detail later, quantum fluctuations, the inherent uncertainty and randomness at the subatomic scale, were stretched to cosmic proportions by the rapid expansion of space. These quantum seeds, amplified by gravity over billions of years, became the galaxies and galaxy clusters we see today. It is one of the most profound connections in all of science. The largest structures in the universe owe their existence to the smallest scales of physics. The spectrum of the cosmic microwave background, the way its intensity varies with frequency, is a near-perfect black-body spectrum. A blackbody is an idealized object that absorbs all electromagnetic radiation that falls on it and emits radiation with a characteristic spectrum that depends only on its temperature. When scientists measured the spectrum of the CMB using the FIRES instrument on the COBE satellite in the early 1990s, they found that it matches a blackbody at a temperature of 2.725 Kelvin so perfectly that it is the most precise blackbody spectrum ever observed in nature. The deviation from a perfect blackbody is less than 50 parts per million. This is an extraordinary result, because it tells us that the early universe was indeed in a state of near-perfect thermal equilibrium, exactly as the Big Bang theory predicts. No other known process in the universe can produce such a perfect blackbody spectrum. This is one of the reasons the CMB is considered such powerful evidence for the Big Bang. Now that we have a solid understanding of what the cosmic microwave background is, let us talk about one of the most delightful stories in the history of science, how it was discovered. Because the discovery of the CMB is a story of brilliant predictions that were ignored, serendipitous accidents, pigeon droppings, and the kind of cosmic irony that only real life can produce. The story begins in the late 1940s when a Ukrainian-American physicist named George Gamow, along with his colleagues Ralph Alpher and Robert Herman, made a remarkable prediction. They were working on the theory of Big Bang nucleosynthesis, trying to understand how the lightest elements, hydrogen, helium, and lithium, were forged in the first few minutes after the Big Bang. In the course of their calculations, they realized that if the Big Bang theory was correct, the hot radiation that filled the early universe should still exist today, cooled down by the expansion of the universe to a temperature of just a few degrees above absolute zero. They predicted that this radiation should be detectable as a faint microwave signal coming from every direction in the sky. Alpher and Herman specifically estimated the temperature would be about 5 Kelvin, which is remarkably close to the actual measured value of 2.725 Kelvin. It was a stunning prediction. If anyone had gone out and built a detector to look for this radiation in the late 1940s or early 1950s, they would have found it. But nobody did. The prediction was largely ignored by the scientific community, partly because Gamow's reputation had been somewhat tarnished by other less successful ideas, and partly because the technology to detect such a faint signal was not yet readily available. The prediction sat there, gathering dust, for more than 15 years. And then, in 1964, something remarkable happened at Bell Telephone Laboratories in Holmdel, New Jersey. Two young radio astronomers, Arno Penzias and Robert Wilson, were working with a large, horn-shaped antenna that had been originally built for satellite communication experiments with the Echo and Telstar satellites. They had repurposed the antenna for radio astronomy, planning to measure the intensity of radio waves coming from the Milky Way and other celestial sources. But when they began their observations, they encountered a problem. There was a persistent, unwanted noise in their data, a constant, low-level hiss that they could not get rid of. This noise was coming from every direction in the sky, at every time of day and night, regardless of where they pointed the antenna. It was not coming from New York City. It was not coming from any known astronomical source. It was not caused by the electronics of the antenna itself. It was just there, uniform, persistent, and completely unexplained. Penzias and Wilson spent months trying to eliminate this noise. They tested and retested their equipment. They cooled the antenna's receiver to reduce thermal noise. They checked every cable, every connection, every component. They even discovered that a pair of pigeons had built a nest inside the horn of the antenna and had coated it with what Penzias delicately described as a white dielectric material. In plain language, pigeon droppings. They cleaned out the droppings, removed the pigeons, and tried again. The noise was still there. The pigeons came back. They removed the pigeons again, more permanently this time. The noise was still there. It would not go away. At this point, Penzias and Wilson were baffled. They had done everything they could think of to eliminate the noise, and nothing had worked. They were seriously worried that their experiment might be flawed, that they would have to abandon their research program because of this mysterious, inexplicable signal. Meanwhile, just about 60 kilometers away, at Princeton University, a team of physicists led by Robert Dicke was independently working on the very problem that Gamow, Alpher, and Hermann had considered decades earlier. Dicke, along with Jim Peebles, P.G. Roll, and David Wilkinson, had independently predicted the existence of the cosmic microwave background and were actually building a detector to search for it. They were on the verge of beginning their observations when Penzias happened to mention his noise problem to a colleague, who knew about Dicke's work and suggested that Penzias call him. Penzias called Dicke. And, in one of the most famous moments in the history of physics, Dicke listened to Penzias describe the mysterious noise, hung up the phone, turned to his colleagues and said, "Boys, we've been scooped." The noise that Penzias and Wilson had been desperately trying to eliminate was the cosmic microwave background radiation, the afterglow of the Big Bang itself. They had accidentally discovered the most important piece of evidence in the history of cosmology while trying to study something else entirely. They had found the echo of creation while cleaning pigeon droppings off an antenna. The two teams published their results simultaneously in the Astrophysical Journal in 1965. Penzias and Wilson's paper was a modest, cautious account of their measurement. They had detected an excess antenna temperature of about 3.5 Kelvin that they could not account for. Dicke's team published a companion paper explaining what it meant. This was the predicted thermal radiation from the Big Bang. The impact was seismic. Before the discovery of the CMB, the Big Bang theory was just one of several competing models for the origin of the universe. Its main rival was the steady-state theory, championed by Fred Hoyle, Hermann Bondi, and Thomas Gold, which proposed that the universe has existed forever, in roughly the same state, with new matter continuously being created to fill in the gaps as the universe expands. The steady-state theory was elegant and philosophically appealing, and it had substantial support in the scientific community. Ironically, it was Fred Hoyle himself who coined the term Big Bang, and he meant it as a mockery, a dismissive label for what he considered a ridiculous theory. He never imagined that the name would stick and become the standard terminology. But the discovery of the CMB effectively killed the steady-state theory. The steady-state model had no way to explain this uniform, all-pervading microwave radiation. It was not predicted by the theory, and there was no mechanism within it that could produce it. The Big Bang theory, on the other hand, had predicted exactly this radiation, with approximately the right temperature more than 15 years before it was discovered. The case was overwhelming. Within a few years, the Big Bang theory had moved from being one hypothesis among several to being the standard model of cosmology, accepted by the vast majority of the scientific community. Penzias and Wilson were awarded the Nobel Prize in Physics in 1978 for their discovery. Gamow, Alpher, and Hermann, who had predicted the CMB decades earlier, received no Nobel recognition, one of the most commonly cited examples of injustice in the history of the Nobel Prize. Gamow had died in 1968, but Alpha and Hermann lived to see the full significance of their prediction confirmed, and the credit go largely to others. Science, for all its grandeur, can sometimes be remarkably unfair. Now, let me pause here and ask you something. Did you know this story before? Did you know that the most important discovery in cosmology, the discovery that confirmed the origin of the universe, happened because two guys were trying to get rid of noise in their antenna and thought pigeon droppings might be the problem? It is one of my favorite stories in all of science because it perfectly illustrates something profound about how scientific discovery actually works. The biggest breakthroughs do not always come from carefully planned experiments. Sometimes they come from confusion, frustration, and sheer accident. Sometimes the universe reveals its deepest secrets to people who are not even looking for them. Drop a comment right now and tell me what is the most surprising scientific discovery you have ever heard of. I'm genuinely curious. And if you are enjoying this deep dive so far, hit that like button. It really does make a difference. It helps this video reach more people who love science, and it tells the algorithm that this kind of content matters. All right, let us keep going, because we have so much more ground to cover. Now that we understand what the cosmic microwave background is and how it was discovered, we need to understand the theory it supports, the Big Bang theory itself. And I want to be very precise here because there are a lot of misconceptions about the Big Bang, and clearing them up is essential for understanding why the CMB anomalies are so significant. First, let me address the single biggest misconception about the Big Bang. The Big Bang was not an explosion. When most people hear the phrase Big Bang, they imagine a massive explosion happening at some point in space, with matter and energy flying outward into some pre-existing void. That is completely wrong. The Big Bang was not an explosion in space. It was an expansion of space. There is a crucial difference. In an explosion, material moves outward from a central point into surrounding space. In the Big Bang, space itself was expanding. There was no center, no edge, no surrounding void. The expansion was happening everywhere, simultaneously, at every point in the universe. Every point in space was moving away from every other point. Not because the matter was flying apart through space, but because the space between the matter was stretching. Imagine baking a loaf of raisin bread. As the bread rises and expands, the raisins all move apart from each other. But no raisin is at the center of the expansion, and no raisin is moving through the bread. The bread itself, the space between the raisins, is what is expanding. The Big Bang is like that, except it is happening in 3 dimensions, and the bread is the fabric of space-time itself. Second, the Big Bang theory does not tell us what caused the Big Bang. It does not tell us why the universe began. It does not tell us what came before the Big Bang. And in fact, the very concept of before may not even make sense, because if time itself began with the Big Bang, then there was no before. The Big Bang theory is not a theory of the origin of the universe in the deepest philosophical sense. It is a theory of the evolution of the universe from an extremely hot, dense, rapidly expanding state. It tells us what happened from a fraction of a second after the beginning, but it does not tell us about the beginning itself. This distinction is important, and we will return to it later. Third, the Big Bang theory is more accurately called the hot Big Bang model, because its key claim is that the universe was once much hotter and denser than it is now, and has been cooling and thinning ever since. The evidence for this is overwhelming, and it comes from multiple independent lines of observation. The expansion of the universe, the cosmic microwave background, and the observed abundances of the lightest elements all point to the same conclusion. Let me now take you through the timeline of the universe, from the very first instant to the present day, because understanding this timeline is essential for understanding what the cosmic microwave background is telling us and why the anomalies are so troubling. The story begins at time zero, the moment of the Big Bang itself. What happened at time zero? The honest answer is, we do not know. Our current theories of physics break down at this point. The densities and temperatures were so extreme that general relativity, our best theory of gravity, and quantum mechanics, our best theory of the subatomic world, both fail. To describe the very first instant of the universe, we would need a theory of quantum gravity, a theory that unifies general relativity and quantum mechanics, and we do not yet have one. String theory, loop quantum gravity, and other approaches are all attempting to develop such a theory, but none has yet succeeded in a complete and testable way. The origin of the universe remains one of the deepest unsolved problems in physics. The first meaningful timescale in the history of the universe is the Planck time, which is approximately 10 to the power of negative 43 seconds, or a decimal point followed by 42 zeros and then a 1. This is an unimaginably short interval of time, far shorter than anything we could ever hope to measure directly. Before the Planck time, during what is called the Planck epoch, the four fundamental forces of nature, gravity, the strong nuclear force, the weak nuclear force, and electromagnetism, are believed to have been unified into a single force. The temperatures were on the order of 10 to the power of 32 Kelvin, a number so large that it is essentially meaningless in everyday terms. We have no theory that can reliably describe what happened during the Planck epoch. It is the ultimate frontier of human knowledge, a realm where our physics simply stops working. After the Planck time, we enter the grand unification epoch, lasting from about 10 to the power of negative 43 seconds to about 10 to the power of negative 36 seconds. During this epoch, gravity separates from the other three forces, becoming its own distinct force. The other three forces, strong, weak, and electromagnetic, remain unified in a single, grand unified force. The temperatures are still absurdly high, on the order of 10 to the power of 28 Kelvin. This epoch is described, at least in theory, by grand unified theories, although none of these theories has yet been experimentally confirmed. Then comes what may be the single most important event in the entire history of the universe, cosmic inflation. From approximately 10 to the power of negative 36 seconds to 10 to the power of negative 32 seconds, the universe underwent a period of incredibly rapid exponential expansion. During inflation, the universe expanded by a factor of at least 10 to the power of 26, perhaps much more, in a tiny fraction of a second. To put this in perspective, a region of space smaller than a proton expanded to a size larger than the entire observable universe in less than a billionth of a billionth of a billionth of a second. This is not an exaggeration. This is what the theory of inflation predicts, and the evidence, particularly from the cosmic microwave background, strongly supports it. Inflation was proposed by Alan Guth in 1981. And it was later refined by Andre Linde, Andreas Albrecht, Paul Steinhardt, and others. It was invented to solve three major puzzles that the original Big Bang theory could not explain. The first puzzle is the horizon problem. When we look at the cosmic microwave background, we see that it has almost exactly the same temperature in every direction. But here's the problem. Regions of the CMB on opposite sides of the sky are separated by about 90 billion light-years today. In the standard Big Bang model without inflation, these regions were never in causal contact. There was never enough time for light or any signal to travel between them. So, how can they be at the same temperature? It is like walking into a room and finding that the air in the far left corner is exactly the same temperature as the air in the far right corner. but you know for certain that no heat exchange has ever occurred between those two corners. It makes no sense unless something happened to put them in contact before they were separated. That something is inflation. Before inflation, the region that would become our observable universe was incredibly tiny, small enough that everything in it was in thermal contact and had reached the same temperature. Then inflation expanded that tiny, uniform region to cosmic scales, explaining why the CMB appears so uniform today. The second puzzle is the flatness problem. Observations show that the geometry of the universe is very close to flat, meaning that the rules of Euclidean geometry, the geometry you learned in school, apply on the largest scales. Parallel lines remain parallel. The angles of a triangle add up to 180 degrees, and so on. But in the standard Big Bang model, a flat universe is incredibly unstable. Any tiny deviation from perfect flatness in the early universe would have been amplified over time, resulting in a universe that is either wildly curved, either positively curved like a sphere, or negatively curved like a saddle. The fact that the universe is flat today, after 13.8 billion years of expansion, requires that it was flat to an extraordinary degree of precision at the beginning, a fine-tuning of about 1 part in 10 to the power of 60. This seems like an absurd coincidence, unless there is a mechanism that drives the universe toward flatness. Inflation provides exactly this mechanism. During the exponential expansion, any curvature in space was stretched out, just like the surface of a balloon becomes flatter as you inflate it. After inflation, the universe was driven extremely close to flatness, exactly as observed. The third puzzle is the magnetic monopole problem. Many grand unified theories predict the existence of magnetic monopoles, hypothetical particles that carry isolated north or south magnetic poles. Unlike ordinary magnets, which always have both a north and south pole, a magnetic monopole would have only one. Grand unified theories predict that monopoles should have been produced in enormous quantities in the early universe, and they should be so massive and abundant that they would dominate the energy density of the universe today. But we have never observed a magnetic monopole, not a single one. Where did they all go? Inflation solves this problem by diluting them. Even if monopoles were produced before inflation, the exponential expansion of the universe would have spread them out so thinly that the probability of finding even one in our observable universe is essentially zero. Inflation solves all three of these problems elegantly and naturally. But it also makes very specific predictions about the cosmic microwave background, predictions that have been tested with extraordinary precision. And this is where the story gets really interesting, because while inflation's predictions match the CMB beautifully in many respects, there are specific areas where the match is not perfect. And those imperfections are the anomalies we are going to explore. After inflation ends, the energy that drove the exponential expansion is converted into particles and radiation in a process called reheating. The universe is now filled with a hot, dense plasma of quarks, gluons, leptons, and photons. As the universe continues to expand and cool, it passes through several more epochs. In the quark epoch, from about 10 to the power of negative 12 seconds to about 10 to the power of negative 6 seconds, the universe is filled with a quark-gluon plasma, a state of matter in which quarks and gluons roam freely, unconfined by the strong nuclear force. When the temperature drops to about 2 trillion Kelvin, the quarks become confined into protons and neutrons, particles collectively known as hadrons. This transition, called the QCD phase transition, marks the beginning of the hadron epoch. By the time the universe is about 1 second old, the temperature has dropped to about 10 billion Kelvin, and we enter the era of Big Bang nucleosynthesis. This is one of the great triumphs of the Big Bang theory. In the first few minutes after the Big Bang, protons and neutrons fuse together to form the nuclei of the lightest elements. Hydrogen, which is just a single proton, deuterium, which is a proton and a neutron, helium-3, helium-4, and tiny traces of lithium-7. The Big Bang theory makes very specific predictions about the relative abundances of these elements, about 75% hydrogen, about 25% helium-4, with trace amounts of deuterium and lithium. These predictions have been tested by measuring the abundances of these elements in the oldest, most primitive regions of the universe, and the agreement is remarkable. The observed abundances match the Big Bang predictions to a degree that would be essentially impossible if the theory were wrong. After nucleosynthesis, the universe continues to expand and cool for several 100,000 years. During this time, it remains a hot plasma of electrons, nuclei, and photons, with the photons constantly scattering off the free electrons. Then, at about 380,000 years, as we discussed earlier, the temperature drops to about 3,000 Kelvin. Electrons combine with nuclei to form neutral atoms, and the universe becomes transparent. The cosmic microwave background is released. This is the moment we see when we look at the CMB, the surface of last scattering, the boundary between the opaque and transparent universe. After the release of the CMB, the universe enters the Dark Ages, a period of several 100 million years during which there are no stars, no galaxies, and no sources of visible light. The universe is filled with neutral hydrogen and helium gas, slowly cooling and gradually clumping together under the influence of gravity. Then, around 200 million to 400 million years after the Big Bang, the first stars ignite. These are the population 3 stars, the first generation of stars, made entirely of hydrogen and helium, with no heavier elements. They are thought to have been massive, hundreds of times the mass of our Sun, and extremely hot and luminous. Their ultraviolet radiation begins to ionize the surrounding neutral hydrogen, starting the process of reionization that eventually makes the universe transparent to visible and ultraviolet light again. Over the next several billion years, galaxies form, merge, evolve, and organize themselves into the large-scale cosmic web, a vast network of filaments and voids that defines the structure of the universe on the grandest scales. Stars live and die, forging heavier elements in their cores and scattering them into space through supernovae. New generations of stars form from this enriched material, eventually giving rise to rocky planets, complex chemistry, and, at least on one small blue world orbiting an ordinary yellow star, life. That is the story of the universe, from the Big Bang to the present day, as told by the standard Big Bang model, or more formally, the lambda CDM model. Lambda refers to the cosmological constant, the mathematical term that represents dark energy, the mysterious force that is accelerating the expansion of the universe. CDM stands for cold dark matter, the invisible, unknown substance that makes up about 25% of the universe's total energy density and provides the gravitational scaffolding for galaxy formation. The lambda CDM model is the standard model of cosmology, the theoretical framework that describes the origin, evolution, and large-scale structure of the universe. And at its heart, the CMB is the most important single piece of evidence supporting it. The Big Bang theory, in the form of the lambda CDM model, makes 3 very specific predictions about the cosmic microwave background, and these predictions are what makes the anomalies so significant. The first prediction is that the CMB should exist at all, as thermal radiation with a near-perfect blackbody spectrum at a temperature of a few degrees Kelvin. This has been confirmed with spectacular precision. The second prediction is that the CMB should have tiny temperature fluctuations, on the order of 1 part in 100,000, with a specific statistical pattern. The fluctuations should follow a Gaussian random distribution, meaning they should be randomly distributed with no preferred locations, directions, or patterns. This has been confirmed to a remarkable degree, but not perfectly, and the deviations are exactly what we are going to talk about. The third prediction is that the CMB should be statistically isotropic, meaning that its statistical properties should be the same in every direction. There should be no preferred axis, no preferred hemisphere, no large-scale patterns that single out any particular direction in the sky. The universe should look the same in every direction, at least statistically. This is a consequence of the cosmological principle, the foundational assumption of modern cosmology, which states that the universe is homogeneous, the same everywhere, and isotropic, the same in every direction, when averaged on sufficiently large scales. The cosmological principle is not just a convenience. It is built into the very mathematical framework of the theory. The lambda CDM model is based on the Friedmann-Lemaitre-Robertson-Walker, or FLRW, metric, which is the mathematical description of a universe that is perfectly homogeneous and isotropic. If the universe is not isotropic, the FLRW metric does not apply, and the entire mathematical foundation of modern cosmology has to be reconsidered. These are the predictions, and for a long time they appeared to be perfectly confirmed. But then the satellites came, and they changed everything. The first dedicated satellite mission to study the cosmic microwave background was COBE, the Cosmic Background Explorer, launched by NASA in 1989. COBE carried 2 key instruments. The first was FIRAS, the Far Infrared Absolute Spectrophotometer, which measured the spectrum of the CMB and confirmed that it is a near-perfect blackbody at 2.725 Kelvin, exactly as predicted. The second was DMR, the Differential Microwave Radiometer, which produced the first all-sky map of the CMB's temperature fluctuations. The resolution was limited, like looking at the universe through frosted glass, but it was enough to confirm that the fluctuations existed, that they were on the right scale, and that they were consistent with the Big Bang model. George Smoot and John Mather, the principal investigators of the DMR and FIRAS instruments respectively, were awarded the Nobel Prize in Physics in 2006 for this work. When the first COBE results were announced, Stephen Hawking reportedly called it the greatest discovery of the century, if not of all time. It was a moment of scientific triumph. The Big Bang had been confirmed with an entirely new kind of evidence, and cosmology had entered a new era of precision. But COBE's resolution was limited. Its map of the CMB was blurry, showing only the largest scale features. To see the finer details, to test the predictions of the Big Bang with greater precision, and to measure the cosmological parameters that define the universe, a more sensitive instrument was needed. That instrument was WMAP, the Wilkinson Microwave Anisotropy Probe, launched by NASA in 2001. WMAP was a revelation. It produced the first detailed, high-resolution, full-sky map of the cosmic microwave background, with angular resolution about 35 times better than COBE. For the first time, scientists could see the fine structure of the CMB's temperature fluctuations, the intricate patterns of hot and cold spots that encode information about the early universe's density, composition, and geometry. WMAP's results were a spectacular triumph for the lambda CDM model. The data confirmed the age of the universe at 13.77 billion years, give or take about 40 million years. It determined the composition of the universe with unprecedented precision. About 4.6% ordinary matter, about 24% dark matter, and about 71.4% dark energy. It confirmed that the geometry of the universe is flat to within 1%. It measured the angular power spectrum of the CMB, the pattern of how the temperature fluctuations vary with angular scale on the sky, and found that it matches the lambda CDM predictions beautifully. But there was something else in the WMAP data. Something that was not supposed to be there. Something that made cosmologists uncomfortable, but that most of them initially tried to ignore or explain away. When scientists analyzed the largest scale patterns in the CMB, the patterns that correspond to the longest wavelengths and the lowest multipole moments in the mathematical decomposition, they found something strange. These large-scale patterns were not randomly oriented. They appeared to be aligned with each other, and even more disturbingly, they appeared to be aligned with the plane of our solar system's orbit around the Sun. This was completely unexpected. The CMB is supposed to be a snapshot of the universe at 380,000 years old, billions of years before the solar system existed. There should be absolutely no connection between the orientation of the large-scale CMB patterns and the geometry of our solar system. And yet, there it was. This was the first clear hint that something might be wrong with the standard picture. But the scientific community was cautious. UMAP's data, while much better than COBE's, still had limitations. Perhaps the alignment was a statistical fluke. Perhaps it was caused by contamination from the Milky Way, which WMAP had to carefully subtract from its data. Perhaps there was some subtle systematic error. Most cosmologists decided to wait for better data before drawing any conclusions. That better data came from Planck. The European Space Agency's Planck satellite, launched in 2009, was the most sensitive and highest resolution CMB mission ever flown. It observed the CMB at 9 different frequency bands, from 30 to 857 gigahertz, allowing for unprecedented separation of the CMB signal from foreground contamination by the Milky Way and other sources. Its angular resolution was about 2.5 times better than WMAP, and its sensitivity was about 10 times greater. Planck produced the definitive map of the cosmic microwave background, the most detailed portrait of the infant universe that humanity has ever created. Planck's results confirmed the lambda CDM model to extraordinary precision. The cosmological parameters were nailed down to the percent level. The angular power spectrum matched the theoretical predictions beautifully over a wide range of scales. It was, in many ways, another triumph for the Big Bang theory. But Planck also confirmed the anomalies. Every strange feature that WMAP had hinted at was still there in the Planck data, now measured with greater precision and higher confidence. The alignments were real. The asymmetries were real. The cold spot was real. These were not artifacts of WMAP's limitations. They were genuine features of the cosmic microwave background. And the Planck team, to their credit, acknowledged this openly. In their official publications, they described the anomalies as features that are not easily explained within the standard lambda CDM framework, and that deserve further investigation. The scientific community could no longer look away. The anomalies were real, and they demanded explanation. And that is where we are going now, into the heart of the mystery, into the anomalies themselves. One by one, we are going to explore each of the major anomalies in the cosmic microwave background, understand what they are, why they are problems for the Big Bang theory, what explanations have been proposed, and what the latest research says about them. And by the time we are done, you will understand why this is one of the most important and exciting frontiers in all of modern physics. But before we get into the anomalies, I want to hear from you again. How many of you already knew about the cosmic microwave background before watching this video? How many of you knew that COBE, WMAP, and Planck had mapped the afterglow of the Big Bang? And how many of you knew that there are anomalies in that afterglow that scientists cannot explain? Drop a comment and let me know. And if you are learning something new, if this video is expanding your understanding of the universe, please share it with a friend who loves science. Just send them the link. It takes 2 seconds, and it means the world to me. Science education should be for everyone, and the more people we can reach with content like this, the better. Let us build a community of curious minds who are not afraid to ask the big questions and go deep to find the answers. All right, let us begin with the anomalies. And we are going to start with perhaps the most visually dramatic and emotionally unsettling of them all. The CMB cold spot. Imagine you are looking at a map of the cosmic microwave background. It is an oval-shaped projection of the entire sky, covered in tiny splotches of slightly warmer, shown in red and yellow, and slightly cooler, shown in blue and green regions. The variations are incredibly small, just a few hundred millionths of a degree, but they are there, and they encode the history of the early universe. The map looks random, which is exactly what the Big Bang theory predicts. There should be no special features, no unusually large hot or cold regions, no patterns that stand out from the random noise. It should look like cosmic static. But if you look carefully at the southern sky, in the direction of the constellation Eridanus, you will see something that should not be there. A large, unusually cold region that stands out from the surrounding sky like a bruise on the face of the universe. This is the CMB cold spot, and when it was first identified in the WMAP data in 2004 by the Spanish astronomer Patricio Vielva and his colleagues, it sent a shiver through the cosmological community. The cold spot is large, spanning about 5 degrees on the sky, which corresponds to about 10 times the apparent diameter of the full moon. In physical terms, it corresponds to a region of space that is approximately 1.8 billion light-years across. And it is anomalously cold, about 70 microkelvin, that is 70 millionths of a degree, colder than the average CMB temperature. This might sound like an absurdly tiny difference, but in the context of the CMB, where the total range of temperature fluctuations is only about 200 microkelvin, a 70 microkelvin deficit in a single, coherent region of this size is genuinely remarkable. To understand why the cold spot is a problem, we need to think about statistics. The Big Bang theory, combined with inflation, predicts that the CMB fluctuations should be drawn from a Gaussian random field. This means that the fluctuations should follow a normal distribution, a bell curve, and large, coherent features should be extremely rare. You would expect small fluctuations to be common and large fluctuations to be rare, just as you would expect most people to be close to average height and only a very few to be extremely tall or extremely short. When scientists calculated the probability of a cold spot as large and as cold as the one observed occurring by random chance in a Gaussian random CMB sky, they found it was only about 1 to 2%. In other words, in a universe that follows the standard Big Bang model with Gaussian fluctuations, you would only expect to see a feature like the cold spot in about 1 or 2 out of every 100 randomly generated CMB skies. This is not overwhelmingly improbable, and by itself it would not be enough to reject the standard model. But it is unusual enough to warrant serious attention, especially when combined with the other anomalies. The first and most natural explanation proposed for the cold spot was that it is caused by a supervoid, an unusually large and unusually empty region of space. In 2007, astronomers discovered that there is indeed a large supervoid, known as the Eridanus supervoid, roughly aligned with the cold spot. A supervoid could in principle cause a cold spot in the CMB through a mechanism called the integrated Sachs-Wolfe effect. Here's how it works. When a CMB photon travels through a normal region of space, it enters gravitational potential wells created by clusters of galaxies and dark matter, gaining energy as it falls in, and then climbs out, losing energy. In a static universe, the energy gained and lost would exactly cancel out, and the photon's temperature would be unchanged. But in an expanding universe with dark energy, the potential wells are getting shallower over time. So by the time the photon climbs out of a well, the well is slightly shallower than when the photon fell in, and the photon retains a small net gain in energy. This makes the CMB appear slightly warmer in the direction of matter concentrations. The opposite happens for voids. A photon entering a void loses a small amount of energy because the void is getting shallower, less negative, as the universe expands. The photon comes out of the void with slightly less energy than it went in with, making the CMB appear slightly cooler in the direction of the void. This is the integrated Sachs-Wolfe effect, and it is a well-understood prediction of the standard cosmological model. The question is whether the Eridanus supervoid is large enough and empty enough to account for the entire observed temperature deficit of the cold spot, and the answer, based on extensive analysis, is probably not. The supervoid contributes some cooling, certainly, but detailed calculations suggest it can account for only a fraction, perhaps 20 to 30%, of the observed temperature deficit. The cold spot is simply too cold and too large to be fully explained by a supervoid of the observed size. This was confirmed by a detailed study in 2022 using data from the Dark Energy Survey, and further analyses in 2025 from the Eridanus Supervoid research team reached similar conclusions. Some scientists have argued that the cold spot is simply a rare, but possible, statistical fluctuation, a 1 in 50 or 1 in 100 event that happened to occur in our particular universe. After all, if you look at enough sky, you are bound to find something unusual somewhere, the so-called look elsewhere effect. This is a perfectly legitimate statistical argument, and it cannot be dismissed out of hand. However, even after correcting for the look elsewhere effect, the cold spot remains anomalous at a level that most statisticians would consider noteworthy, if not definitive. And then there's the wild explanation, the truly extraordinary, boundary-pushing, paradigm-shattering explanation. In 2007, Laura Mersini Houghton at the University of North Carolina proposed that the cold spot could be the imprint of a collision between our universe and another universe in the multiverse. To understand this idea, we need to briefly discuss eternal inflation and the multiverse. In many versions of inflation theory, the process of inflation does not end everywhere at the same time. Instead, inflation ends in some regions while continuing in others, creating an endlessly expanding sea of inflating space punctuated by bubbles, where inflation has ended and a normal, slowly expanding universe has formed. Our observable universe would be one such bubble. Other bubbles, other universes would be forming all the time, endlessly, forever. This is the eternal inflation scenario, and it naturally gives rise to the concept of the multiverse, a vast, perhaps infinite collection of universes, each with potentially different physical laws, different constants of nature, different numbers of spatial dimensions. If two of these bubble universes collide, the collision would leave a mark on the cosmic microwave background. The collision would create a circular or nearly circular region on the CMB with a distinctive temperature profile, either hotter or colder than the surrounding sky. Laura Mersini Houghton and her collaborators argued that the cold spot has the right characteristics to be such a mark. Think of it this way. Imagine the surface of a soap bubble. If another soap bubble pushes up against it, the point of contact deforms the surface. The cold spot, in this interpretation, is where another universe pushed against ours during the earliest moments of cosmic history, leaving a permanent dent in the fabric of space-time that we see today as an anomalous cold region in the CMB. This is a breathtaking idea. If it is correct, the cold spot is not just an anomaly in the data. It is evidence for the existence of the multiverse. It is a scar on the face of our universe left by a collision with another reality. It would mean that our universe is not alone, that there are other universes out there, perhaps infinitely many, each one a separate reality with its own history, its own laws of physics, its own possibilities. I need to be clear, this explanation is highly speculative. It has not been confirmed, and most cosmologists are extremely cautious about it. A study by the Royal Astronomical Society in 2017 examined the cold spot in detail and concluded that while the supervoid explanation was insufficient, the evidence was also insufficient to confirm the multiverse hypothesis. The study acknowledged that the multiverse explanation could not be ruled out, but emphasized that much more work was needed. As of 2025 and 2026, the cold spot remains one of the biggest open questions in cosmology. It is too cold and too large to be easily explained by known mechanisms, but the data is not yet precise enough to definitively confirm or rule out the more exotic explanations. Future observations from the Euclid satellite and other upcoming surveys may finally resolve this mystery, one way or another. But here is what makes the cold spot truly fascinating. Even if it turns out to have a mundane explanation, the fact that it exists at all reminds us that the universe still has secrets. The cosmic microwave background, for all its beautiful agreement with theory, is not a closed book. It is a text that we are still learning to read, and the cold spot is a passage that we cannot yet translate. Now, let us move on to the second anomaly, and this one has perhaps the most dramatic name in all of cosmology. It is called the axis of evil. I am not making that up. That is its actual name in the scientific literature. It was coined by the cosmologists Kate Land and João Magejo of Imperial College London in a paper published in 2005. And the name has stuck because it perfectly captures the sense of dread that this anomaly inspires in anyone who cares about the foundations of cosmology. To understand the axis of evil, we need to talk about how scientists analyze the cosmic microwave background mathematically. The CMB temperature map is a function defined on the surface of a sphere, the celestial sphere, the imaginary sphere surrounding us in all directions. To analyze this function, cosmologists decompose it into what are called spherical harmonics, which are the natural mathematical basis functions for any function on a sphere. This is analogous to how a musical sound can be decomposed into its component frequencies using Fourier analysis. Just as a complex musical note can be broken down into a sum of pure tones, the complex pattern of temperature fluctuations on the CMB sky can be broken down into a sum of spherical harmonics, each characterized by a multipole number, usually denoted by the letter L. The lowest multipole, L equals 1, is the dipole, which divides the sky into two halves, one warmer and one cooler. As we will discuss later, the CMB dipole is well understood and is caused by our motion through the universe. The next multipole, L equals 2, is the quadrupole, which divides the sky into four regions. Then L equals 3 is the octupole, which divides the sky into 8 regions, and so on, with higher multipoles corresponding to increasingly fine-scale patterns on the sky. According to the Big Bang theory, each multipole should be randomly oriented. There should be no preferred direction in the sky, no alignment between different multipoles. The orientation of the quadrupole should have nothing to do with the orientation of the octupole, which should have nothing to do with the orientation of any other multipole. This is a direct consequence of statistical isotropy, the principle that the universe looks the same in every direction. But when scientists looked at the quadrupole and octupole of the CMB, first in the WMAP data and later confirmed by Planck, they found something deeply troubling. The quadrupole and octupole are aligned with each other. Their preferred axes, the directions that define their orientation on the sky, point in roughly the same direction. Moreover, both of them are approximately aligned with the ecliptic, which is the plane of Earth's orbit around the Sun, and they are also roughly aligned with the direction of the equinoxes, the points where the ecliptic crosses the celestial equator. Let me emphasize how strange this is. The cosmic microwave background is a snapshot of the universe at 380,000 years old. The solar system formed about 4.6 billion years ago, roughly 9 billion years after the CMB was released. There should be absolutely zero connection between the large-scale patterns in the CMB and the geometry of the solar system. The probability of the quadrupole-octupole alignment occurring by random chance has been estimated at roughly 1%, similar to the cold spot. But the additional alignment with the ecliptic makes it even more improbable. This is why it is called the axis of evil. The name is a tongue-in-cheek reference to the fact that this alignment is evil for cosmology, because it directly challenges the assumption of statistical isotropy that underlies the entire Standard Model. If the universe truly has a preferred direction, a cosmic axis that coincides with the geometry of our solar system, then either something is very wrong with our understanding of the universe, or something is very wrong with our data. Let us consider the possible explanations for the axis of evil, because there are several, and they range from the mundane to the revolutionary. The first and most conservative explanation is that the alignment is caused by residual contamination from foreground sources, particularly the Milky Way galaxy. The CMB signal has to be carefully separated from the microwave emission of our own galaxy, which produces its own microwave radiation from interstellar dust, synchrotron radiation from electrons spiraling in magnetic fields, and other sources. If the foreground subtraction is not perfect, residual contamination could create spurious patterns in the CMB that happen to align with the galactic plane, which is not far from the ecliptic plane on the sky. This explanation has been extensively tested. Both the WMAP and Planck teams performed detailed analyses using multiple foreground subtraction methods, different frequency channels, and different galactic masks, and the alignment persists regardless. The Planck team specifically concluded that the foreground contamination explanation was unlikely to account for the observed alignment. This does not completely rule it out, because there could always be some subtle, unknown systematic effect, but it makes it considerably less plausible. The second explanation is that the alignment is a statistical coincidence. With only one universe to observe, there is always a chance that unusual things happen. The probability of the quadrupole-octupole alignment is roughly 1%, which is unusual but not overwhelmingly so. Maybe we just got unlucky. Maybe the universe rolled the dice and came up with an improbable result. This is always a valid possibility in science, and it is impossible to completely rule out. But scientists are generally uncomfortable with explanations that rely on improbable coincidences, especially when the same data contains multiple independent anomalies that all point in a similar direction. The third explanation involves the topology of the universe. If the universe has a non-trivial topology, meaning it is finite in some directions and wraps around on itself, like the surface of a torus or a dodecahedron, then the large-scale patterns in the CMB could have preferred directions that reflect the geometry of the universe's shape. A famous proposal along these lines was the Poincaré dodecahedral space model, suggested by Jean-Pierre Luminet and colleagues in 2003, which proposed that the universe has the shape of a regular dodecahedron with opposite faces identified. This model could in principle explain some of the large-scale CMB anomalies, including the low quadrupole power and the alignments. However, subsequent analysis of the Planck data found that the specific predictions of the dodecahedral model were not confirmed, although more general topological models have not been completely ruled out. The fourth explanation involves anisotropic inflation. If inflation itself was not perfectly isotropic, if the exponential expansion was slightly different in different directions, it could have imprinted a preferred direction on the CMB that persists to this day. This is an active area of research, and several specific models of anisotropic inflation have been proposed. However, most of these models introduce additional free parameters that must be fine-tuned to match the observed anomalies, which diminishes their explanatory power. The fifth and most radical explanation is that the alignment with the ecliptic is telling us something truly fundamental about our place in the universe. Some researchers have suggested that the alignment could be evidence that the Copernican principle, the idea that our location in the universe is not special, is wrong. Perhaps there is something about our specific location, or the specific region of the universe we inhabit, that creates these alignments. This is an uncomfortable idea for most scientists, because the Copernican principle has been one of the guiding assumptions of science for centuries, and abandoning it would require a radical rethinking of our place in the cosmos. As of the most recent analyses, the axis of evil remains unexplained. It has been confirmed by multiple independent datasets and analysis methods, and no single explanation has gained widespread acceptance. It is one of the most persistent and troubling anomalies in modern cosmology, and it continues to inspire both skepticism and wonder in roughly equal measure. Now, let us move on to the third anomaly, the hemispherical power asymmetry. This anomaly is closely related to the axis of evil, and when you put them together, the picture that emerges is deeply unsettling. The hemispherical power asymmetry is exactly what it sounds like. When you divide the CMB sky into two hemispheres, one half has slightly more power, that is, slightly stronger temperature fluctuations than the other half. The hemisphere with more power is roughly in the direction of the constellation Leo, and the hemisphere with less power is in the opposite direction. The asymmetry is about 6 to 7%, meaning that the fluctuations in the stronger hemisphere are about 6 to 7% larger in amplitude than in the weaker hemisphere. 6 to 7% might not sound like much, but remember, the Big Bang Theory predicts that the CMB should be statistically isotropic, the same in every direction. There should be no preferred hemisphere. The fluctuations should have the same statistical properties regardless of which half of the sky you look at. A 6 to 7% asymmetry on the largest scales is not what the theory predicts, and while it is not overwhelmingly large, it is consistently detected in both the WMAP and Planck data with a statistical significance that is difficult to dismiss. The hemispherical power asymmetry was first reported in the WMAP data in the early 2000s and was subsequently confirmed by Planck with higher precision. The direction of the asymmetry, the axis that separates the stronger hemisphere from the weaker one, is roughly aligned with the axis of evil, which is deeply suggestive. It means that the same preferred direction that shows up in the quadrupole-octupole alignment also shows up in the hemispherical power asymmetry. Two independent anomalies, measured in different ways, pointing in the same direction. This is not the kind of thing that happens easily by coincidence. Several explanations have been proposed for the hemispherical power asymmetry. One possibility is that there exists a perturbation on a scale larger than the observable universe, a superhorizon perturbation that modulates the amplitude of the CMB fluctuations across the sky. If our observable universe is embedded in a larger region of space that has a large-scale gradient in some property, such as the amplitude of primordial fluctuations, this could create an apparent asymmetry within our visible patch of the sky. This is sometimes called the tilted universe model, and it is a natural prediction of some inflationary models that produce fluctuations on scales much larger than the observable universe. Another possibility is anisotropic dark energy. If dark energy, the mysterious force that is accelerating the expansion of the universe, has a directional component, if it is stronger in one direction than another, it could create a hemispherical asymmetry in the CMB. This is a speculative idea, and there is no independent evidence for anisotropic dark energy, but it remains a theoretical possibility. A third possibility is that the asymmetry is related to the same pre-inflationary physics that might explain the axis of evil. If conditions before inflation were not perfectly symmetric, if there was some anisotropy in the quantum state of the universe before inflation began, it could have been amplified and imprinted on the CMB. But perhaps the most significant recent development related to the hemispherical power asymmetry is the work on the cosmic dipole anomaly, which takes us to the fourth and arguably most fundamental anomaly in the cosmic microwave background. This is the one that has the potential to truly shatter the standard cosmological model. In December 2025 and January 2026, a team led by Subir Sarkar, an emeritus professor at the University of Oxford, published research that sent shockwaves through the cosmological community. Their work concerns a test so fundamental, so basic, so central to the standard model of cosmology that its failure would have profound implications for our entire understanding of the universe. It is called the Ellis-Baldwin test, and to understand it, we need to talk about the CMB dipole. The CMB dipole is the largest temperature variation in the cosmic microwave background. If you look at a full sky map of the CMB, the most prominent feature is a smooth gradient from one side of the sky to the other. One direction is slightly warmer, about 3.36 millikelvin above average, and the opposite direction is equally cooler. This dipole, this smooth, warm, cool gradient, is by far the largest signal in the CMB, much larger than the tiny fluctuations we have been discussing. The standard explanation for the CMB dipole is simple and well understood. It is caused by our motion through the universe. The solar system, along with the Milky Way galaxy and the entire local group of galaxies, is moving through space at a speed of about 370 kilometers per second in the direction of the constellation Leo. This motion creates a Doppler effect. In the direction we are moving toward, the CMB photons are blue-shifted, meaning they appear to have slightly higher energy and thus a higher temperature. In the direction we are moving away from, the photons are red-shifted, meaning they appear to have lower energy and a lower temperature. This is exactly analogous to how the pitch of a siren changes as an ambulance drives toward you and then away from you. This explanation is universally accepted, and by itself the CMB dipole is not an anomaly. It is a straightforward consequence of our motion through the CMB rest frame. But here is where it gets interesting, and where the potential crisis emerges. In 1984, two cosmologists named George Ellis and John Baldwin proposed a clever test of the standard cosmological model. They reasoned as follows. If the CMB dipole is caused by our motion, then the same motion should also create a corresponding dipole in the distribution of distant astronomical sources, such as radio galaxies and quasars. Here is why. If we are moving toward one direction in space, then distant sources in that direction should appear slightly brighter and more numerous, because of relativistic aberration and Doppler boosting, while sources in the opposite direction should appear slightly dimmer and less numerous. This is a well-understood prediction of special relativity, and the size of the matter dipole, the asymmetry in the distribution of distant sources, can be precisely calculated from the size of the CMB dipole. In other words, if the universe is truly isotropic, and the CMB dipole is caused solely by our motion, then the CMB dipole and the matter dipole must agree. They must point in the same direction and have a specific ratio of amplitudes. This is the Ellis-Baldwin test, and it is one of the most fundamental consistency tests of the standard cosmological model. For decades, this test could not be performed because it requires a large, uniform catalog of very distant astronomical sources, and such catalogs were not available. But in recent years, several such catalogs have become available, and the results are alarming. Study after study, using different datasets and different analysis methods, has found the same thing. The matter dipole is 2 to 5 times larger than what the CMB dipole predicts. The direction is roughly correct, but the amplitude is way off. The universe fails the Ellis-Baldwin test. The variation in the distribution of distant matter does not match the variation predicted by the cosmic microwave background. This has been confirmed using multiple independent datasets. The NVSS, the NRAOVLA Sky Survey, which catalogs radio galaxies detected by the Very Large Array in New Mexico, shows a matter dipole that is about 2 to 3 times the predicted value. The WISE and CatWise 2020 catalogs, based on infrared observations from the Wide Field Infrared Survey Explorer satellite, show a similar excess. Quasar catalogs show the same thing. Each dataset independently, using different types of sources observed at different wavelengths with different instruments, arrives at the same conclusion. The matter dipole is too large. The Oxford team's analysis, published in a paper in Physical Review D, systematically reviewed all available data and concluded that the cosmic dipole anomaly poses a serious challenge to the standard cosmological model. They went further, arguing that the anomaly challenges not just the lambda CDM model but the FLRW description of space-time itself, the very mathematical framework on which all of modern cosmology is built. Let me explain why this is so significant. The other anomalies we have discussed, the cold spot, the axis of evil, the hemispherical asymmetry, are features of the CMB itself. They could potentially be explained by unusual but not impossible statistical fluctuations, or by systematic effects in the CMB data processing. The cosmic dipole anomaly is different. It is a discrepancy between two completely independent types of data: the CMB, observed by satellites in space, and the distribution of matter, observed by terrestrial and space-based telescopes at completely different wavelengths. The possible sources of error are entirely different for these two types of measurements. The fact that they both point to the same conclusion, that the universe is more asymmetric than the standard model predicts, makes the result much harder to dismiss. If the cosmic dipole anomaly is real, and if it cannot be explained by some subtle systematic effect that has so far eluded detection, then the implications are enormous. It would mean that the universe is not isotropic on large scales. It would mean that the cosmological principle, the assumption that the universe looks the same in every direction, is wrong. It would mean that the FLRW metric, the mathematical description of spacetime that underlies the lambda CDM model, does not correctly describe our universe. And that would mean that essentially everything we have derived from the FLRW framework, the age of the universe, the expansion history, the composition in terms of dark matter and dark energy, would need to be reconsidered. As Subir Sarkar himself put it, this is not something that can be patched up by adding a new parameter to the lambda CDM model. It requires going back to square one and reconsidering the most fundamental assumptions of cosmology. I want to pause here for a moment because I realize we have covered 4 massive anomalies in a row, and each one individually is deeply concerning. The cold spot is unexplained. The axis of evil violates statistical isotropy. The hemispherical asymmetry suggests the universe is lopsided, and the cosmic dipole anomaly implies that the entire mathematical framework of modern cosmology may be wrong. But here is the thing that really keeps cosmologists awake at night. These anomalies are not independent. The axis of evil, the hemispherical asymmetry, and the cosmic dipole all point in roughly the same direction in the sky. 3 different measurements using 3 different methods, all suggesting that the universe has a preferred direction that aligns with the ecliptic plane and the constellation Leo. When multiple independent anomalies all point in the same direction, it becomes much harder to dismiss any of them as a coincidence. It suggests that there is something real, something fundamental, something that we do not yet understand, lurking beneath the surface of the cosmic microwave background. And if that is blowing your mind right now, you are not alone. The smartest physicists on the planet are struggling with this. They are lying awake at night wondering whether the universe they have spent their careers studying is fundamentally different from what they assumed. This is not a minor technical issue. This is a potential paradigm shift in how we understand reality. If you are feeling the weight of that, hit that like button. Seriously, it takes 1 second, and it helps this video reach more people who deserve to know about this. And drop a comment telling me which anomaly shocked you the most. The cold spot, the axis of evil, the hemispherical asymmetry, the cosmic dipole anomaly. I genuinely want to know what is going through your mind right now. All right, let us push forward, because there is one more anomaly to discuss, and it is perhaps the most recent and most tantalizing of them all. It is called cosmic birefringence, and it was essentially unknown to the general public until very recently, but it may end up being the most important clue of all. To understand cosmic birefringence, we first need to understand a property of light called polarization. Light is an electromagnetic wave, an oscillation of electric and magnetic fields that travels through space. In most cases, the electric field oscillates in random directions, perpendicular to the direction the light is traveling, with no preferred orientation. But light can become polarized, meaning the electric field oscillations are restricted to a single plane. This happens, for example, when light reflects off a flat surface, which is why polarized sunglasses reduce glare, by blocking the horizontally polarized light reflected from roads and water. The cosmic microwave background is partially polarized. This polarization was created by the process of Thomson scattering, the scattering of photons off free electrons in the primordial plasma. The polarization pattern carries information about the conditions in the early universe that is complementary to the temperature information we have been discussing. In particular, the polarization can be decomposed into 2 types, called E modes and B modes, and the detailed pattern of polarization across the sky provides additional constraints on cosmological models. Now, in ordinary physics, once a photon is polarized, the direction of its polarization remains constant as it travels through empty space. A polarized photon emitted 13.8 billion years ago should arrive at our detectors with its polarization direction unchanged. But in 2020, something remarkable was discovered. Yuto Minami, a researcher at the Institute of Particle and Nuclear Studies in Japan, and Eiichiro Komatsu, a renowned cosmologist at the Max Planck Institute for Astrophysics in Germany, analyzed the Planck satellite's polarization data in a novel way. They compared the polarization of the CMB, which was emitted 13.8 billion years ago, with the polarization of microwave light scattered by dust grains in our own Milky Way galaxy, which was emitted much more recently. The Milky Way's dust provides a convenient reference frame for the polarization direction, because its polarization is determined by the local galactic magnetic field, and should not be affected by whatever cosmic process might rotate the CMB's polarization. What Minami and Komatsu found was startling. The polarization plane of the CMB has been rotated by about 0.35 degrees relative to the Milky Way dust polarization. The CMB's polarization is not in the direction it should be. Something has twisted it. This rotation is called cosmic birefringence. In optics, birefringence is a property of certain crystals, like calcite, that have two different refractive indices, causing light passing through them to be split into two rays with different polarizations. When you look through a birefringent crystal, you see a double image. Cosmic birefringence is the same idea, but applied to the entire universe. The polarization of the oldest light in the cosmos has been rotated, as if the universe itself is acting like a giant birefringent crystal. The initial measurement had a statistical significance of about 2.4 sigma, which is suggestive but not conclusive. In scientific terms, a result is generally considered reliable at 3 sigma and definitive at 5 sigma. So 2.4 sigma is interesting but not proof. However, subsequent analyses have strengthened the case. In September 2025, a team using polarization data from the Atacama Cosmology Telescope in Chile measured a rotation angle of about 0.215 degrees, consistent with the Planck result. And in February and March of 2026, additional studies using new data and improved analysis techniques have continued to find evidence for cosmic birefringence, with the statistical significance gradually creeping upward. Now, why is this such a big deal? What does it mean for physics if the CMB's polarization has been rotated? The answer takes us to one of the deepest symmetries in physics, parity symmetry. Parity symmetry is the principle that the laws of physics should be the same if you reflect the entire universe in a mirror. Left and right should be interchangeable. If you built a mirror image of the universe, with every particle replaced by its mirror counterpart, and every process running in the mirror-reflected direction, the laws of physics should still work in exactly the same way. For most of physics, parity symmetry holds. The laws of gravity, electromagnetism, and the strong nuclear force are all parity symmetric. But there is one notable exception: the weak nuclear force, which is responsible for radioactive decay, violates parity. This was demonstrated experimentally in 1957 by Chien-Shiung Wu and her colleagues in one of the most famous experiments in particle physics. The discovery that parity is violated in weak interactions was a shock to the physics community and earned Tsung-Dao Lee and Chen-Ning Yang the Nobel Prize. But until now, parity violation has been observed only in the weak nuclear force, and only at the subatomic scale. Cosmic birefringence, if confirmed, would be the first evidence of parity violation at cosmological scales across the entire observable universe. It would mean that the universe distinguishes between left and right, between clockwise and counterclockwise rotation, on the grandest possible scale. This would be a profoundly important discovery, because it would point to new physics beyond the standard model of particle physics, physics that we have not yet discovered or understood. What kind of new physics could cause cosmic birefringence? Several theoretical models have been proposed, and they all involve fundamentally new ingredients in our description of the universe. The leading candidate is axion-like particles, often abbreviated as ALPs. Axions were originally proposed in the late 1970s to solve a problem in quantum chromodynamics, the theory of the strong nuclear force, called the strong CP problem. The strong CP problem asks why the strong force does not violate the combination of charge conjugation and parity, called CP symmetry, when the theory seems to allow it. The solution, proposed by Roberto Pecce and Helen Quinn, involves introducing a new symmetry that gives rise to a new, very light, very weakly interacting particle, the axion. Axions and axion-like particles are also among the leading candidates for dark matter, the invisible substance that makes up about 25% of the universe's energy density. If axion-like particles exist, they would form a background field that permeates all of space, and this field would interact with photons in a specific way. It would rotate their polarization. This is exactly the effect that cosmic birefringence would represent. A preprint paper from early 2026 proposes that the observed cosmic birefringence can be explained by the superposition of two axion-like particle fields with different masses. The authors show that this model can account for the observed rotation angle while being consistent with other cosmological and astrophysical constraints. If correct, this would be one of the first observational hints of the nature of dark matter, obtained not from a particle physics experiment on Earth, but from the oldest light in the universe. Another possibility is that cosmic birefringence is caused by a quintessence field. Quintessence is a theoretical alternative to the cosmological constant as an explanation for dark energy. While the cosmological constant is a fixed number, the same everywhere and at all times, quintessence is a dynamic field that can vary in space and time. Some quintessence models predict that the field interacts with photons in a way that rotates their polarization, producing cosmic birefringence. A third possibility involves Chern-Simons gravity, a modification of general relativity that includes terms that violate parity symmetry. In Chern-Simons gravity, the left-handed and right-handed polarizations of gravitational waves propagate at slightly different speeds, and a similar effect could occur for electromagnetic radiation, producing cosmic birefringence. And a fourth possibility is rooted in string theory, which predicts the existence of extra spatial dimensions beyond the three we experience. The shapes and configurations of these extra dimensions give rise to a vast landscape of possible physical laws, and some configurations produce fields that interact with photons in parity-violating ways. What all these possibilities have in common is that they involve fundamentally new physics. Cosmic birefringence, if confirmed, cannot be explained within the standard model of particle physics or the standard lambda-CDM model of cosmology. It requires new particles, new fields, new interactions, or new modifications to gravity. It is a window into the deepest levels of physical reality, and it is being opened not by a particle accelerator or a laboratory experiment, but by the oldest light in the universe. The investigation of cosmic birefringence is still in its early stages. The current evidence is suggestive, but not yet definitive. The next major step will come from the LightBird satellite, a Japanese space mission scheduled for launch in the late 2020s, which is specifically designed to measure the CMB's polarization with unprecedented precision. LightBird will either confirm cosmic birefringence at a definitive level of statistical significance, or it will rule it out. Either way, it will be a landmark result. But even now, in 2026, the evidence for cosmic birefringence is one of the most exciting developments in cosmology in years. It connects the largest scales of the universe to the smallest scales of particle physics. It links the cosmic microwave background to dark matter and dark energy, and it suggests that the universe has secrets that we are only just beginning to uncover. Now, I want to take a brief detour from the specific CMB anomalies to discuss something that may at first seem unrelated, but is actually deeply connected to everything we have been talking about. In 2025, a team of researchers from Nanjing University in China and the University of Bonn in Germany published a paper that posed a startling question. What if part of the cosmic microwave background does not come from the Big Bang at all? Their argument goes like this. The standard interpretation of the CMB is that it is entirely primordial, meaning it was produced during the epoch of recombination, 380,000 years after the Big Bang, and has been traveling through space ever since. But the universe has not been empty since then. Stars have formed, galaxies have assembled, and enormous amounts of energy have been released. In particular, the very first galaxies, the massive elliptical galaxies that formed less than 1 billion years after the Big Bang, went through an incredibly intense phase of star formation, producing hundreds of billions of stars in a cosmically short period. This intense star formation produced enormous amounts of radiation and dust. The researchers argued that the radiation from these early elliptical galaxies, scattered and thermalized by the surrounding dust, could have produced a background of microwave radiation with a near blackbody spectrum, essentially mimicking the cosmic microwave background. If this contribution is significant, it would mean that the CMB is not purely primordial. Part of the signal, perhaps a small part, or conceivably a substantial part, could come from the formation of the first galaxies rather than from the Big Bang itself. This is a provocative claim, and the mainstream scientific community has reacted with a mixture of interest and skepticism. The main argument against it is that the CMB's blackbody spectrum is simply too perfect to be explained by astrophysical foregrounds. The FIRS instrument on COBE measured the CMB spectrum to extraordinary precision, and any significant contribution from galaxy formation would likely create detectable deviations from a perfect blackbody. Furthermore, the angular power spectrum of the CMB, the pattern of fluctuations at different scales, matches the Big Bang predictions with such extraordinary precision that it is difficult to see how a significant foreground contribution could be present without being detected. Nevertheless, the paper raises an important point. As our understanding of early galaxy formation evolves, particularly in light of surprising discoveries by the James Webb Space Telescope, showing that galaxies formed earlier and more abundantly than expected, we need to be vigilant about potential foreground contamination of the CMB. Even a small contribution from early galaxy formation could affect the precise measurements of cosmological parameters that we derive from the CMB, and it could, in principle, affect the statistical analysis of the anomalies. This is an active area of research, and future observations from JWST, Euclid, and other instruments will help clarify the contribution of early galaxies to the microwave background. For now, the mainstream consensus remains that the CMB is overwhelmingly primordial, but the question is an important one, and it deserves continued investigation. Now, there is one more piece of the puzzle that we need to discuss before we can put the whole picture together. It is called the Hubble tension, and while it is not strictly a CMB anomaly, it is deeply connected to the CMB and to the broader crisis in cosmology. The Hubble tension is a disagreement between two different measurements of the expansion rate of the universe. The expansion rate is quantified by the Hubble constant, denoted h0, which tells you how fast distant galaxies are moving away from us as a function of their distance. A galaxy that is 1 megaparsec away, about 3.26 million light-years, is receding from us at a speed of h0 kilometers per second. The Hubble constant is one of the most fundamental parameters in cosmology because it determines the scale, age, and ultimate fate of the universe. There are two main ways to measure the Hubble constant. The first uses the CMB. By analyzing the detailed pattern of temperature fluctuations in the CMB, scientists can determine the cosmological parameters of the lambda-CDM model with high precision, and from these parameters they can calculate what the Hubble constant should be. The Planck satellite's measurement gives H0 equals approximately 67.4 kilometers per second per megaparsec. The second method uses direct observations of the nearby universe. By measuring the distances to nearby galaxies using standard candles, objects of known luminosity such as Cepheid variable stars and Type 1a supernovae, astronomers can directly determine the Hubble constant. The most precise measurement using this method, led by Nobel laureate Adam Ress and the SH0ES team, gives H0 equals approximately 73.0 kilometers per second per megaparsec. These two numbers do not agree. The difference is about 8 to 9%, which might seem small, but the measurements are so precise that the disagreement is now at a statistical significance exceeding 5 sigma, the gold standard for discovery in physics. In other words, the probability that this disagreement is due to random chance is less than 1 in 3 million. Something is genuinely wrong. If the Hubble constant from the CMB, which measures the early universe, is different from the Hubble constant from supernovae, which measures the recent universe, then the rate of expansion of the universe is not what the lambda-CDM model predicts. The universe is expanding faster locally than it should be based on the conditions in the early universe. This means either there is a systematic error in one or both measurements, which extensive checking has failed to identify, or there is new physics between the early universe and the present day that the standard model does not account for. The Hubble tension connects to the CMB anomalies in a profound way. Both suggest that the lambda-CDM model is incomplete. The CMB anomalies suggest that the model's fundamental assumptions about isotropy and Gaussianity may be wrong. The Hubble tension suggests that the model's predictions for the expansion history may be wrong. Together, they paint a picture of a theory that is remarkably successful in broad strokes, but is showing cracks at the level of precision measurements. Several explanations have been proposed for the Hubble tension. One is early dark energy, a component of dark energy that was present in the early universe but has since disappeared. If early dark energy existed, it would have changed the expansion rate in the early universe in a way that could reconcile the CMB and local measurements. Another possibility is new neutrino physics, such as additional neutrino species or neutrinos with unexpected properties. A third is modified gravity, changes to the theory of general relativity that affect the expansion history. A fourth is decaying dark matter, where dark matter particles slowly convert into radiation over time, changing the expansion rate. And then there is the most radical possibility. Perhaps the standard cosmological model is simply wrong. Perhaps the assumptions that underlie it, the cosmological principle, the FLRW metric, the nature of dark energy and dark matter, are not correct, and a fundamentally new model is needed. This possibility is not as far-fetched as it might seem. In October 2025, a physicist at Cornell University published calculations showing that if dark energy is not a cosmological constant, but a dynamic field that changes over time, the universe could be headed for a big crunch, a reversal of the expansion that would cause the entire universe to collapse in on itself in about 20 billion years. This connects to results from the Dark Energy Spectroscopic Instrument, DESI, which in 2024 and 2025 reported tantalizing hints that dark energy may indeed be evolving over time. If dark energy is dynamic rather than constant, it would change everything about how we interpret the CMB. The cosmological parameters derived from the Planck data assume a cosmological constant, And if this assumption is wrong, the derived values for the age, composition, and geometry of the universe would all need to be revised. This could also affect the statistical analysis of the CMB anomalies, potentially making some of them more or less significant. We are entering a period of profound uncertainty in cosmology. The Standard Model, which has served us brilliantly for decades, is showing signs of strain. The Hubble tension, the CMB anomalies, the cosmic dipole anomaly, the hints of cosmic birefringence, the Daisy results on dark energy, and the surprising discoveries by the James Webb Space Telescope are all pointing in the same direction. The universe is more complex, more mysterious, and potentially more strange than our current models allow. So, what does all of this mean? Let us step back and try to see the big picture. Let us try to understand what these anomalies, taken together, are telling us about the nature of reality.